Okay guys, let me explain how we are going to implement Dijkstra's algorithm. If you are not familiar with priority queue data structure, this will be somewhat trickier, so focus. Now this is the pseudocode that we are going to implement. Now in this pseudocode, in the line 3, we are going to put all the vertices to data structure called queue. Now this data structure is going to be a different version of queue. But for now, just imagine it's a linked list. Now in the while loop, there are two operations going to change the object in this list. Extract min function which extract the object with minimum distance, and of course relax function which will update the distance of the object in the queue. Now let's analyze the runtime of this pseudocode considering queue is a linked list data structure. So to extract the minimum of linked list, we have to run through all the elements in the linked list, which means one extract min function call will take time proportional to the number of vertices in our linked list data structure. And this for loop in line 7 and 8, all it does is running through all the edges in our graph. So if you consider this while loop, what it does is running through all the vertices, and we are calling relax function in this for loop which will run through adjacency list of particular vertex. So this outer while loop and for loop together represent the run through each edge in our graph. So the runtime complexity for this implementation will be v square plus e. Now this is not much optimized version. So therefore we will not going to use linked list as our queue data structure. Instead we are going to use priority queue data structure. Now you can think of priority queue as a binary tree or binary heap. Now if you are not familiar with the binary heaps, I have provided some resources, so go through those. Now this tree is arranged in a certain way. For any node in this tree, its left child is less than the particular vertex and its right child is greater than the particular vertex. Now if we use priority queue data structure, let's analyze the runtime of this algorithm. So here, one extract min function call will take time proportional to logarithmic v, and we are going to call extract min function for number of vertices time. Therefore, the total time taken by extract min function will be v log v. Now this relax function will update the distance of certain nodes in our tree. So this will result in rearrangement of tree which take log v times. Since this for loop together with the outer while loop will take number of h time, so the total time complexity for relax function call will take e log v time. So the final time complexity will be v plus e log v. Now this is much optimized version than the previous linked list implementation which took v square time complexity. But if we use priority queue data structure, we have another problem to handle here. Priority queue implementation in the standard library will not dynamically update its data structure if the value is changed for the object already in the tree. So if we put all the elements to the priority queue at the beginning, none of this relax function call will be able to update that data structure. So what we are going to do, we are not going to add all the vertices to the priority queue at the beginning. At the beginning, we are going to add only source vertex. And after relax function call, which means after updating each vertex distance, we are going to add it to the priority queue, so it will rearrange in correct order. So in this pseudocode, this third line is going to change, adding all the elements to adding source vertex. And after this relax function call, we are going to add that changed vertex to our priority queue. Now if we add object to priority queue in this way, same object may be included in more than one time. So to discriminate object properly, instead of directly storing vertex, I'm going to store a pair which contains object and newly changed integer value. So let me give you an example of what I am going to follow here. Now consider the table in the left side. Now in this table we have vertex in sorted order. Now if we change this t vertex distance to 5 in the relax function call, it will add another pair which included the t vertex and the newly updated value, and the resultant table is also in a sorted order. Now with this implementation, there's another problem. If we add same vertex multiple times, there's a possibility that we pop same vertex multiple times and call relax on same vertex. Now to handle this multiple object problem, I'm going to have separate Boolean array, and whenever the object popped, we first check if the corresponding slot in this Boolean array is true or false. If it is true, which means the object is already popped, then we skip this current object and pop the next. Otherwise, we will set the corresponding slot to true and proceed with the current object. Okay, this is the overall picture of how I am going to implement this pseudocode. Now, if you are struggling to understand this, I am encourage you to go through the implementation couple of times and come back to this lecture and watch it again. In the next video, we will look at the implementation of this method. Thank you.